Now let's take a look at the deadbeat escapement. The common Graham deadbeat escapement may look similar to a recoil escapement, but there are significant differences. Repairing them can be difficult, as any work done on the escapement will alter the geometry and introduce recoil. Of course, the deadbeat escapement will still work even if the geometry isn't perfect, but the whole point of using the deadbeat escapement in a clock is to leverage its advantages, and this requires attention to detail to obtain results that surpass the recoil escapement. Deadbeat escapements are most commonly used in higher-grade weight-driven clocks and are seldom used in spring-driven clocks because the varying power of the mainspring as it unwinds significantly reduces any benefit gained. Under optimal conditions, a high-grade weight-driven movement, an accurately machined anchor, and running in a temperature-controlled environment, the Graham deadbeat escapement can expect to keep time to 1 second per week or better. This is about 10 times better than a recoil escapement under the same conditions. The Graham deadbeat also requires 1/4 to 1/2 the driving power as the same clock using a recoil escapement. Less drive power means less wear on the movement over time. There are 3 distinct differences between the Graham deadbeat and the recoil escapement. First, the anchor is symmetrical. Both the entry and exit sides of the anchor have the same or very similar shape. Next, there are 2 distinct pallet surfaces on both the entry and exit sides of the anchor. The red arrows extending from the saddle on the anchor point to the curved, dead pallet faces. The center of the radius of the curve of these pallets is the center of rotation of the anchor. An escape wheel tooth riding on this curved surface will appear to stand still as the anchor moves beneath it because the tooth is resting on a perfect circle, with the center of rotation being the center of the circle. The green arrows point to the impulse faces that transfer power to the pendulum to keep it moving. The blue arrows point to the corner or heel that separates the dead faces from the impulse faces. With 2 pallets on each side of the anchor, the deadbeat anchor has a total of 4 pallets. Since the escape wheel teeth initially contact a curved surface, there is no recoil. The escape wheel's movement stops dead, and the escapement locks before moving on to the impulse phase. Last but not least, the tips of the escape wheel teeth point in the direction it rotates. If the escape wheel rotates clockwise, then the escape wheel teeth will point to the right, just the opposite of the recoil escapement. Let's take a look at the deadbeat escapement in action. See how the escape wheel turns in the clockwise direction, or to the right, and the wheel teeth also point to the right? Now let's slow the movement down so we can see what's happening. Notice how the escape wheel moves forward and then comes to a full stop before moving forward again. This full stop is called the lock. The deadbeat escapement does not recoil, it locks. Directly after the lock, we see the escape wheel tooth cross the heel and then slide across the face of the impulse pallet. This is when the escape wheel is giving impulse or energy to the pendulum. When the impulse phase is complete and the escape wheel tooth reaches the end of the impulse pallet, there's a small gap between the dead pallet on the opposite side of the anchor and the new tooth that is ready to strike it. As in the recoil escapement, this gap is called the drop. The tooth giving impulse slides off its pallet and the escape wheel moves rapidly to jump the gap, and the new tooth drops onto the dead pallet face of the opposite side of the anchor. The tooth that just landed on the dead pallet face halts its forward movement as it rides on its curved surface during the overswing of the pendulum, creating the lock, and the cycle starts over again. Drop, lock, impulse. Drop, lock, impulse.